Hello there. In this lecture I'm going to talk a bit about distributed charge, which I'll explain in a second. In previous lectures we talked about point charges, which are just charges that take up no volume in space. Distributed charge, on the other hand, is a bit different because it's spread out over some volume of space. Let's take, for instance, this infinite slab. By infinite, I mean that it extends to the left and right directions and towards you and into the page infinitely. This slab has some charge distributed throughout it. Let's say it's a positive charge, and it's spread out throughout our infinite slab here. For simplicity's sake, let's say that this charge is uniform, which means that it's spread out evenly throughout our slab. So let's talk about electric field. If we've got a positive test charge Q at some point below our infinite slab, we can think about the electric field caused by the charge in the slab. Sometimes it's helpful to partition the distributed charge into little areas with some bit of charge in them. So we can think about this area, for instance, which exerts a force. We know it's repulsive because both of these charges are positive in this direction. So you might be inclined to think that the electrical field points in that direction, but in fact this is not true because there is another little area of charge here that's exerting a force that looks like this. So we'll see that by superposition, the components of the force in this direction and this direction cancel out, so you just end up with a force pointing downwards. This is true throughout the entire slab because the charge is uniformly distributed. This means that the electrical field will be uniform, and because our distributed charge is positive, the electrical field will be pointing outward from our infinite slab. So the electric field will look like this. Now let's talk a little bit about distributing charge in an insulator versus a conductor. Here we've got a spherical conductor, and I'm going to put some charge plus Q on it. This charge is able to move throughout the sphere. It's not just a point charge, it's distributed. So let's see, where is Q going to go? It's able to move freely since this is a conductor. By definition, charge moves freely throughout a conductor. We know that the charge, since it's all positive charge, will be repelling itself. So we would expect that the charge wants to get as far away from all the other charges as possible. This means that the charge will move to the very edges, the surface of our conductor. So you would expect to see a lot of positive charge on the surface. This means that you would see no charge in the middle here. So what does that mean for an electric field? Well, since there's no charge inside, we see no electric field. You can verify this by superposition. We've got forces acting in here and also on the other side all throughout, and you can see that this this force will cancel with this force and so forth. It's a little bit messy. And then on the outside it looks a little bit different. Each charge will exert forces on some imaginary positive test charge to look like this, so you see an electrical field that points radially outward from the center of the conductor. In an insulator, it's a little bit different because the charge cannot move, so you can have some sort of distribution of charge, be it uniform or non-uniform, throughout the insulator. And in this case, you can have an electric field inside the insulator. And in this case, you'll also have an electric field outside of the insulator, but it might be different. So let's recap. You can have charge distributed throughout an insulator or a conductor. In a conductor, you would expect the charge to move to the edges or the surface of the conductor because the charge is repelling itself. In an insulator, the charge cannot move, so it can be distributed throughout the entire volume of the object, so you can get a uniform or a non-uniform charge distribution. That's all.